In the realm of professional software architecture, environment reproducibility is paramount. We recommend the Conda distribution, not just for its convenience, but for its sophisticated package management system. Conda provides a modern data science analytics architecture that supports over 400 popular Python packages out of the box. From a lead architect's perspective, the value lies in its ability to handle complex dependencies across multi-workload data analytics and big data environments. Moving to the interface, we utilize Jupyter Notebook. Jupyter is more than a text editor. It is a web-based REPL, read, eval, print loop interface that facilitates interactive scientific computing. It allows for the seamless integration of live code, narrative text, and rich visualizations. This is critical for data science, where the discovery phase requires constant iteration and immediate feedback. By leveraging Jupyter, we can share contributions and integrate with big data platforms, ensuring that our local development environment mirrors the complexity of production-grade clusters. We will be utilizing Python 3.7 for this series, as it represents the stable standard for modern library compatibility.
Data science relies on numeric precision. Python supports two primary numeric types, integers and floats. While Python 3 handles arbitrary precision integers, floating point numbers are typically implemented using double precision in C, following the IEEE 754 standard. This distinction is vital when performing high-frequency calculations where rounding errors can propagate. Beyond numbers, Python's string processing capabilities are exceptionally robust. Strings are immutable sequences of Unicode characters. We can define them using single, double, or triple quotes, the latter being essential for multi-line strings or docstrings. From a logic perspective, remember that because strings are immutable, every modification actually generates a new string object. Finally, we must discuss typecasting. In a dynamically typed language, explicit casting using functions like int, float, or string is our primary tool for ensuring data consistency. For instance, when ingesting data from a CSV, all values may initially be strings. We must cast them to floats to perform mathematical modeling. This transformation is the first step in any data wrangling pipeline.
The choice between a tuple and a list is an architectural decision based on mutability. A tuple is a one-dimensional, immutable sequence. Once defined, its elements and their order cannot be changed. This makes tuples faster and memory efficient, ideal for fixed data like coordinate pairs or database records. Conversely, a list is mutable. We can append, remove, or insert items at runtime. Under the hood, Python lists are dynamic arrays, meaning they over-allocate memory to ensure that append operations are O of 1 amortized. However, inserting an element at the beginning of a large list is O of n because every subsequent element must be shifted. Both structures support slicing, a powerful feature for data extraction. The syntax list 1 to 4 retrieves elements from index 1 up to, but not including, index 4. This is a shallow copy operation. Understanding that the stop index is exclusive is a common point of friction for beginners, but aligns with zero-based indexing logic used across most modern systems. Use tuples for data integrity and lists for dynamic data collection. Moving to unordered structures, the dictionary, or dict, is perhaps the most important data structure in Python. It is a hash map that stores key-value pairs. The architectural requirement for a dictionary key is that it must be hashable, meaning it must be immutable, like a string or a tuple. This allows for O1 average time complexity for lookups, making dictionaries incredibly efficient for large-scale data indexing. We can view keys and values independently, or modify them using the update method. Parallel to this is the set. A set is an unordered collection of unique elements. It is essentially a dictionary with only keys and no values. Sets are the go-to structure when you need to eliminate duplicates or perform set theory operations. As shown in our code examples, the pipe operator denotes a union, combining all unique elements from two sets, while the ampersand denotes an intersection, finding only the commonalities.
In data engineering, sets are frequently used to filter unique identifiers across massive datasets before joining tables.
Python utilizes operator overloading to provide a consistent interface across different data types. The in operator is a prime example. It performs membership testing. In a list, this is an O of n linear search, but in a set or dictionary, it is an O of 1 hash lookup. This is a critical performance distinction for any software architect. The plus operator is overloaded for sequences to perform concatenation. Whether you are joining two strings, two lists, or two tuples, the plus operator produces a new object containing the combined elements. Similarly, the star operator does not perform mathematical multiplication on sequences. Instead, it performs repetition. For example, friend times 3 results in friend, friend, friend. While these operators are syntactically elegant, be cautious. Concatenating large lists in a loop using plus creates a new list object in every iteration, leading to O of n squared complexity. In such cases, using the .join method for strings or .extend for lists is the architecturally superior choice to minimize memory reallocations.
Functions are the primary method of code organization in Python. Defined using the def keyword, they are first-class objects, meaning they can be passed as arguments to other functions. A key architectural consideration is the return value. If no return is specified, the function implicitly returns none. Python also supports multiple return values by packing them into a tuple, as seen in our profile function example. To write truly Pythonic code, one must master built-in sequence functions. Enumerate is essential for loops where you need both the index and the value, avoiding the anti-pattern of range len of x. Zip allows you to iterate over multiple sequences in parallel, pairing elements into tuples. This is highly efficient for merging disparate data columns. Finally, we have sorted and reversed. Note that sorted returns a new list, leaving the original sequence intact, which is preferred in functional programming patterns to avoid side effects. These utilities form the basis of clean, readable, and efficient data processing logic.
The final layer of our foundation is control flow. Python uses if, elif, and else for conditional branching. Unlike many languages, Python relies on indentation to define block scope, which enforces readability. For iteration, the for loop is used to traverse collections or iterators. We use continue to skip the current iteration and break to exit the loop entirely, crucial for optimizing search algorithms. However, real-world data is messy, and robust programs must handle errors gracefully. This is where exception handling comes in. Instead of allowing a value error to crash your data pipeline when a string cannot be converted to a float, we wrap the logic in a try-except block. This allows the program to catch the error, log it, and continue processing. From a lead architect's perspective, this is the EAFP principle, easier to ask for forgiveness than permission. It is often more efficient to attempt an operation and handle the failure than to perform expensive pre-checks on every data point. This concludes our technical deep dive into the essentials.